We have the last talk of the day to wrap up, and this is a fantastic thing because Moritz will tell about the actual application of AI and what he's doing with Tenstorrent hardware on drug discovery. And yeah, I've just learned like it was like a hobby project, or it was a hobby project last year, and now he's working at Tenstorrent to continue his work. So like hobby project turned into a job, and a good one with a passion. This is awesome. So like let's listen to what you want to say about the progress of your project.
Awesome, thanks. I'm going to give a little update on my project TT-Boltz. I actually gave already a talk at the second edition of the AI Plumber conference about TT-Boltz, but that was still like Boltz-1 on Tenstorrent wormhole, and really a lot has happened since then, and so I thought it would be like cool to give a little update. So for people who are not already familiar with the project, TT-Boltz is basically a port of Boltz-2 to Tenstorrent hardware, and Boltz-2 is a biomolecular structure prediction model, and basically just improved successor of AlphaFold 3, and I think like more people are familiar with AlphaFold than Boltz. But actually like Boltz became industry standard, and so all the biotech labs use Boltz and not AlphaFold anymore. And yeah, the project is completely open source under the MIT license, and it works out of the box on Tenstorrent hardware. And I started the project in November 24, just as my pet project, as a side project during university. And then in April 25, I had the first working prototype, and since then I was just optimizing the model. And after I finished my studies, I joined Tenstorrent now, and I get a lot of time to work on the project and more resources, which is awesome. And I also wrote my thesis about this topic, so if anyone is interested, you can also check out the repo and the thesis. Yeah, but first I want to talk a little bit about Tenstorrent hardware, but want to keep it really brief because like there were so many talks about Tenstorrent hardware. So here we have the Tenstorrent black hole P150, which is currently the most performant PCI Express card that is available in the shop. And yeah, in the middle we have the black hole processor, then 8 GDDR6 memory banks with 4 GB each, so 32 gigabytes. But for me, like the coolest thing is that it has a large SRAM, 210 megabytes of SRAM, and it's a scratch pad, so we can control it explicitly. And stay for a long time in SRAM for certain operations, which can be a major advantage against like, or in comparison with GPUs who have like transparent caches that you can only control implicitly. On the right is my quiet box. And yeah, the Boltz project right now is only running on a single card, but very soon we want to parallelize it across multiple cards. There's also a Tenstorrent Galaxy server with like 32 processors, and yeah, I want to like leverage everything for drug discovery on the Boltz project. Yeah, here's the architecture of the black hole processor and the 10-6 core. So black hole processor, the architecture is basically just a grid of cores. We have Ethernet cores, DRAM cores, system controller, but where actually the compute happens, that's the 10-6 cores. And on the right we have the architecture of 10-6 cores, and we have 5 small RISC-V chips, and they basically control the routers, and the data movement and compute engines, and each 10-6 core has also, I think on black hole, 1.5 megabytes of SRAM. Yeah, but I think not everyone here is familiar with structure prediction. So proteins are basically the building blocks of life. They underpin all processes in life, and they are defined by a sequence of amino acids. And this sequence of amino acids folds into a 3D structure in the human body, and the 3D structure determines the function, what the protein does in the human body. So it is really important to predict the structure, and that was a huge problem for 50 years in biology. And AlphaFold 2 basically solved this problem and therefore was awarded the Nobel Prize in 2024, and it can predict those structures in minutes and not years. Boltz-2 builds on top of AlphaFold, but it adds also affinity prediction there in the top right corner. And affinity prediction predicts basically the probability and how strong a small molecule binds to a protein. And for example, a protein could be a harmful protein, and then you want to design a drug, so a small molecule, the ligand here, that attaches to the protein and maybe disables this function. And that's why binding affinity is so important for drug discovery. And yeah, in contrast to AlphaFold, the Boltz model is fully open source and not only for academic usage. In the bottom we have the whole architecture of the Boltz-2 model. It can seem pretty complex, but the most important modules are really just the performer in the middle, the diffusion model, and maybe also the MSA module. So formally it is basically just a diffusion module, but it is a pretty unique diffusion module because most of the computational complexity is in this performer, which is a transformer. And yeah, that's what makes it different from, pretty different from other diffusion modules. This is another way of looking at the architecture, and there we can see that Boltz-2 basically consists of a few number of big modules which are composed of smaller modules, and the main big modules are the performer diffusion module and the MSA module. And we can, for example, see that the template module, the confidence module, and the affinity module are just thin wrappers around the performer. And so the task of porting the Boltz model to Tenstorrent hardware was just porting those big modules to the Tenstorrent architecture. And yeah, I would say the most interesting small modules are triangle multiplication and triangle attention, and they have cubic complexity, not just quadratic complexity, in contrast, for example, to regular self-attention. And the triangle comes from the fact that between those atoms, the triangle inequality holds, and that is just inductive bias. And that's basically what the researchers did with AlphaFold and Boltz. It feels like engineering inductive biases. So they take regular machine learning operations, but they have some requirements from, for example, physics, and they have to engineer those inductive biases in the model. And another interesting thing about the Boltz-2 model are the activations. So we have a single representation. This is a usual representation, for example, in transformers. In transformers, we have a sequence of tokens, and therefore a sequence of embeddings, and therefore this matrix on the left. But additionally, in the Boltz-2 model, we have a pair representation, and this pair representation has additional dimension, which is as large as the sequence length. And this is the root cause for this increased complexity. This means, for example, that the activations, the memory complexity of the activations are quadratic in sequence length. And so for larger molecules, most of the memory is consumed by the activations and not the weights. The Boltz-2 model is actually a pretty small module, but the activations can get really large. And this is also this additional dimension, which is as large as the sequence length, is also the root cause for the increase for the cubic time complexity of triangle attention and triangle multiplication. And yeah, that's basically the skeleton how I ported Boltz to Tenstorrent hardware. Those are just two of the big modules, but I just rewrote them in TTNN, then put them in a PyTorch wrapper, so from the outside they look like PyTorch modules, and then I could use it in the existing code base. And then, yeah, most of my time was actually spent on performance optimizations, and the key performance optimization that I did across all those modules was for triangle attention, I integrated flash attention 2. I will dive deeper into that later. Then, of course, like always, fusing operations. For example, if you compute queries, keys, and values. You have 3 linear transformation, but you can fuse them into one. Then you have a bigger matrix multiplication. That means higher arithmetic intensity, and so you can utilize the matrix units more. But in general, just fusing operations, having less kernel overhead, staying longer in SRAM, that was important. And since the activations have high memory complexity, I use chunking a lot. So processing those activations, those tensors in chunks that we also can keep in SRAM. That was really important. And of course, mixed precision. So by default, we use bfloat 16. But whenever we can, whenever it doesn't affect the accuracy too much, we use block FP8. And for example, for triangle attention, we can basically do all of it in block FP8. And because triangular attention is one of the most interesting small modules, I just wanted to give briefly the idea how we used regular flash attention 2 for that. And we have here the standard attention formula, and in the standard attention formula we add attention mask. And in triangle attention we just have to replace the attention mask with a triangle bias. And there's a small difference between the attention mask and the triangle bias. The attention mask is the same for all attention heads, so we can broadcast it across the head dimension. But the triangle bias is actually different per head, but we have to broadcast it across the batch dimension. And so the first trick that we did was just permuting the head dimension and the batch dimension because they are both independent. But even those permutations took too long, and so in the end we just added support for batch broadcasting to the flash attention kernel, and this way we can just use flash attention 2 for triangle attention. And now I want to talk a little bit about the evaluation, about the performance. This is, of course, just the baseline, so Boltz-2 on a CPU and Boltz-2 on black hole. And yeah, we can see that it is significantly faster than a CPU for all sequence length. And with sequence length, I always mean the number of amino acids in a protein. More interesting is, of course, the comparison with a GPU, and so I wanted to compare the best PCI Express cards from NVIDIA and from Tenstorrent that are available for consumers, but of course just comparing the inference time would be a little unfair because the average over the last year of RTX 5090 were $3,000. Right now it's not even available for this price. Tenstorrent card is significantly faster, and if we look at the predicted structures per hour per dollar, we have better results for the Tenstorrent cards for all proteins except the one with more than 1,000 amino acids. But I still think that there's a bug for large proteins, and I hope we can solve it and also get better for larger proteins. So I think Tenstorrent cards already have very good price performance, and for small proteins, the Tenstorrent black hole card is actually faster than an RTX 5090. And when optimizing the performance, profiling is of course very important, and looking at how the runtime is distributed across all sequence length. And I think across all the big modules. And I think the most interesting thing is here that as the sequence length increases, the performer more and more dominates the runtime, and that's because only the performer contains triangle attention and triangle multiplication, which are the only small modules that have cubic complexity. And so for large proteins, we mostly care about the performer, but for small proteins, it's also very important to optimize, for example, the diffusion module. And that's basically how a predicted structure looks like. This protein structure, the blue protein structure, was predicted on a Tenstorrent black hole card. In green we have the experimental ground truth, And so, yeah, it is pretty accurate, and that's also confirmed by all the important metrics. And I guess we still have a little bit of time, so I can also hopefully show a little demo. Or did it crash? Oh, maybe I have to start it again. Yeah, so I think it works now. So the first part was generating the MSA. Then it is loading the module into the memory. Then the performer runs, and right now that is the diffusion module. And you can see how the protein is folded in real time. That was pretty fast. And then you can also see, for example, for each amino acids here, how confident the model is in the prediction or the overall confidence, and some metrics that are important for biology. So I think with that we can open up for Q&A maybe.
Yeah. On the comparison, is the NVIDIA running on FP32 and TT and Tenstorrent on bfloat16 or base?
The NVIDIA card is also running on BF16. Yeah, the NVIDIA card is also running on BF16, but they don't use block FP8 anywhere.
Questions? Okay, good. Thank you very much. This is a wrap. I'll give it to. Thank you.
Thanks.
Okay, thank you everybody for joining us today. So if you want to continue these discussions, you can join us also on Monday on the Fringe event. You can also just continue to the breweries and continue the evening. Thank you everyone.